The Byzantine Generals Problem. The Byzantine Generals Problem is a generalization of the so-called two generals problem, which imagines a situation in which two army generals need to agree on a battle plan. As they have set up camp on two different sites, they can only communicate by messenger, and the messengers sometimes get delayed or lost like packets in a network. We will discuss this problem of consensus in Chapter 9. In the Byzantine version of the problem, there are generals who need to agree, and their endeavor is hampered by the fact that there are some traitors in their midst. Most of the generals are loyal, and thus send truthful messages, but the traitors may try to deceive and confuse the others by sending fake or untrue messages while trying to remain undiscovered. It is not known in advance who the traitors are. Byzantium was an ancient Greek city that later became Constantinople, in the place which is now Istanbul in Turkey. There isn't any historic evidence that the generals of Byzantium were any more prone to intrigue and conspiracy than those elsewhere. Rather, the name is derived from Byzantine in the sense of excessively complicated, bureaucratic, devious, which was used in politics long before computers. Lamport wanted to choose a nationality that would not offend any readers, and he was advised that calling it the Albanian Generals Problem was not such a good idea. A system is Byzantine fault-tolerant if it continues to operate correctly even if some of the nodes are malfunctioning and not obeying the protocol, or if malicious attackers are interfering with the network. This concern is relevant in certain specific circumstances. For example, in aerospace environments, the data in a computer's memory or CPU register could become corrupted by radiation, leading it to respond to other nodes in arbitrarily unpredictable ways. Since a system failure would be very expensive, for example an aircraft crashing and killing everyone on board, or a rocket colliding with the International Space Station, flight control systems must tolerate Byzantine faults. In a system with multiple participating organizations, some participants may attempt to cheat or defraud others. In such circumstances, it is not safe for a node to simply trust another node's messages, since they may be sent with malicious intent. For example, peer-to-peer networks like Bitcoin and other blockchains can be considered to be a way of getting mutually untrusting parties to agree whether a transaction happened or not, without relying on a central authority. However, in the kinds of systems we discuss in this book, we can usually safely assume that there are no Byzantine faults in your data center. All the nodes are controlled by your organization, so they can hopefully be trusted, and radiation levels are low enough that memory corruption is not a major problem. Protocols for making systems Byzantine fault-tolerant are quite complicated, and fault-tolerant embedded systems rely on support from the hardware level. In most server-side data systems, the cost of deploying Byzantine fault-tolerant solutions makes them impractical. Web applications do need to expect arbitrary and malicious behavior of clients that are under end-user control, such as web browsers. This is why input validation, sanitization, and output escaping are so important to prevent SQL injection and cross-site scripting. For example, however, we typically don't use Byzantine fault-tolerant protocols here, but simply make the server the authority on deciding what client behavior is and isn't allowed. In peer-to-peer networks, where there is no such central authority, Byzantine fault tolerance is more relevant. A bug in the software could be regarded as a Byzantine fault, but if you deploy the same software to all nodes, then a Byzantine fault-tolerant algorithm cannot save you. Most Byzantine fault-tolerant algorithms require a supermajority of more than 2/3 of the nodes to be functioning correctly, i.e., if you have 4 nodes, at most one may malfunction. To use this approach against bugs, you would have to have 4 independent implementations of the same software and hope that a bug only appears in one of the 4 implementations. Similarly, it would be appealing if a protocol could protect us from vulnerabilities, security compromises, and malicious attacks. Unfortunately, this is not realistic either. In most systems, if an attacker can compromise one node, they can probably compromise all of them, because they are probably running the same software. Thus, traditional mechanisms, authentication, access control, encryption, firewalls, and so on continue to be the main protection against attackers. Although we assume that nodes are generally honest, it can be worth adding mechanisms to software that guard against weak forms of lying, for example, invalid messages due to hardware issues, software bugs, and misconfiguration. Such protection mechanisms are not full-blown Byzantine fault tolerance, as they would not withstand a determined adversary, but they are nevertheless simple and pragmatic steps toward better reliability. For example, network packets do sometimes get corrupted due to hardware issues or bugs in operating systems, drivers, routers, etc. Usually, Corrupted packets are caught by the checksums built into TCP and UDP, but sometimes they evade detection. Simple measures are usually sufficient protection against such corruption, such as checksums in the application-level protocol. A publicly accessible application must carefully sanitize any inputs from users, for example checking that a value is within a reasonable range, and limiting the size of strings, to prevent denial of service through large memory allocations. An internal service behind a firewall may be able to get away with less strict checks on inputs, but some basic sanity checking of values, for example in protocol parsing, is a good idea. NTP clients can be configured with multiple server addresses. When synchronizing, the client contacts all of them, estimates their errors, and checks that a majority of servers agree on some time range. As long as most of the servers are okay, a misconfigured NTP server that is reporting an incorrect time is detected as an outlier and is excluded from synchronization. The use of multiple servers makes NTP more robust than if it only uses a single server. System model and reality. Many algorithms have been designed to solve distributed systems problems. For example, we will examine solutions for the consensus problem in Chapter 9. In order to be useful, these algorithms need to tolerate the various faults of distributed systems that we discussed in this chapter. Algorithms need to be written in a way that does not depend too heavily on the details of the hardware and software configuration on which they are run. This in turn requires that we somehow formalize the kinds of faults that we expect to happen in a system. We do this by defining a system model, which is an abstraction that describes what things an algorithm may assume. With regard to timing assumptions, 3 system models are in common use. Synchronous model. The synchronous model assumes bounded network delay, bounded process pauses, and bounded clock error. This does not imply exactly synchronized clocks or zero network delay. It just means you know that network delay, pauses, and clock drift will never exceed some fixed upper bound. The synchronous model is not a realistic model of most practical systems, because as discussed in this chapter, unbounded delays and pauses do occur. Partially synchronous model. Partial synchrony means that a system behaves like a synchronous system most of the time, but it sometimes exceeds the bounds for network delay, process pauses, and clock drift. This is a realistic model of many systems. Most of the time, networks and processes are quite well behaved, otherwise we would never be able to get anything done, but we have to reckon with the fact that any timing assumptions may be shattered occasionally. When this happens, network delay, pauses, and clock error may become arbitrarily large. A synchronous model. In this model, an algorithm is not allowed to make any timing assumptions. In fact, it does not even have a clock, so it cannot use timeouts. Some algorithms can be designed for the asynchronous model, but it is very restrictive. Moreover, besides timing issues, we have to consider node failures. The 3 most common system models for nodes are crash stop faults. In the crash stop model, an algorithm may assume that a node can fail in only one way, namely by crashing. This means that the node may suddenly stop responding at any moment, and thereafter that node is gone forever, it never comes back. Crash recovery faults. We assume that nodes may crash at any moment, and perhaps start responding again after some unknown time. In the crash recovery model, nodes are assumed to have stable storage, i.e. non-volatile disk storage, that is preserved across crashes, while the in-memory state is assumed to be lost. Byzantine arbitrary faults. Nodes may do absolutely anything, including trying to trick and deceive other nodes, as described in the last section. For modeling real systems, the partially synchronous model with crash recovery faults is generally the most useful model. But how do distributed algorithms cope with that model? To define what it means for an algorithm to be correct, we can describe its properties. For example, the output of a sorting algorithm has the property that for any 2 distinct elements of the output list, the element further to the left is smaller than the element further to the right. That is simply a formal way of defining what it means for a list to be sorted. Similarly, we can write down the properties we want of a distributed algorithm to define what it means to be correct. For example, if we are generating fencing tokens for a lock, see fencing tokens on page 303, we may require the algorithm to have the following properties. Uniqueness. No 2 requests for a fencing token return the same value. Monotonic sequence. If request X return token TX, and request Y return token TI, and X completed before Y began, then TX TI. Availability. A node that requests a fencing token and does not crash eventually receives a response. An algorithm is correct in some system model if it always satisfies its properties in all situations that we assume may occur in that system model. But how does this make sense? If all nodes crash, or all network delays suddenly become infinitely long, then no algorithm will be able to get anything done. To clarify the situation, it is worth distinguishing between two different kinds of properties: safety and liveness properties. In the example just given, uniqueness and monotonic sequence are safety properties, but availability is a liveness property. What distinguishes the two kinds of properties? A giveaway is that liveness properties often include the word eventually in their definition. And yes, you guessed it, eventual consistency is a liveness property. Safety is often informally defined as nothing bad happens, and liveness is something good eventually happens. However, it's best to not read too much into those informal definitions, because the meaning of good and bad is subjective. The actual definitions of safety and liveness are precise and mathematical. If a safety property is violated, we can point at a particular point in time at which it was broken. For example, if the uniqueness property was violated, we can identify the particular operation in which a duplicate fencing token was returned. After a safety property has been violated, the violation cannot be undone, the damage is already done. A liveness property works the other way round. It may not hold at some point in time. For example, a node may have sent a request but not yet received a response, but there is always hope that it may be satisfied in the future, namely by receiving a response. An advantage of distinguishing between safety and liveness properties is that it helps us deal with difficult system models. For distributed algorithms, it is common to require that safety properties always hold in all possible situations of a system model. That is, even if all nodes crash or the entire network fails, the algorithm must nevertheless ensure that it does not return a wrong result, i.e., that the safety properties remain satisfied. However, with liveness properties we are allowed to make caveats. For example, we could say that a request needs to receive a response only if a majority of nodes have not crashed, and only if the network eventually recovers from an outage. The definition of the partially synchronous model requires that eventually the system returns to a synchronous state, that is, any period of network interruption lasts only for a finite duration and is then repaired. Safety and liveness properties and system models are very useful for reasoning about the correctness of a distributed algorithm. However, when implementing an algorithm in practice, the messy facts of reality come back to bite you again, and it becomes clear that the system model is a simplified abstraction of reality. For example, algorithms in the crash recovery model generally assume that data in stable storage survives crashes. However, what happens if the data on disk is corrupted, or the data is wiped out due to hardware error or misconfiguration? What happens if a server has a firmware bug and fails to recognize its hard drives on reboot, even though the drives are correctly attached to the server? Quorum algorithms see quorums for reading and writing on page 179 rely on a node remembering the data that it claims to have stored. If a node may suffer from amnesia and forget previously stored data, that breaks the quorum condition, and thus breaks the correctness of the algorithm. Perhaps a new system model is needed, in which we'd assume that stable storage mostly survives crashes, but may sometimes be lost. But that model then becomes harder to reason about. The theoretical description of an algorithm can declare that certain things are simply assumed not to happen, and in non-Byzantine systems, we do have to make some assumptions about faults that can and cannot happen. However, a real implementation may still have to include code to handle the case where something happens that was assumed to be impossible, even if that handling boils down to print sucks to be you and exit 666, i.e. letting a human operator clean up the mess. This is arguably the difference between computer science and software engineering. That is not to say that theoretical, abstract system models are worthless, quite the opposite. They are incredibly helpful for distilling down the complexity of real systems to a manageable set of faults that we can reason about, so that we can understand the problem and try to solve it systematically. We can prove algorithms correct by showing that their properties always hold in some system model. Proving an algorithm correct does not mean its implementation on a real system will necessarily always behave correctly, but it's a very good first step, because the theoretical analysis can uncover problems in an algorithm that might remain hidden for a long time in a real system, and that only come to bite you when your assumptions, for example about timing, are defeated due to unusual circumstances. Theoretical analysis and empirical testing are equally important.